Mirrors are common, everyday objects that fascinate us by creating perfect duplicates of our surroundings. But have you ever paused to wonder how a simple object is capable of capturing your image with such clarity? The secret lies in the molecular interactions and the laws of physics that govern light. At the foundation of a mirror's functioning is the physics of light and reflection. Light travels in a straight line unless it is refracted, absorbed, or reflected. When light reaches a smooth, reflective surface, like a mirror, it is reflected, which means it bounces back rather than being absorbed or transmitted. The molecular magic happens in the mirror's coating, typically a thin film of metal such as silver or aluminum. These metals are chosen for their high reflectivity, which is due to the nature of their electron structure. Metals have free electrons, the so-called sea of electrons, that are not bound to any particular atom and can move freely throughout the metal's structure. When photons, or particles of light, strike the surface of the mirror, the electromagnetic field of the photon interacts with the sea of electrons. This interaction causes the electrons to oscillate, and they then re-radiate the light energy. Mirrors are designed in such a way that the re-radiated light is emitted in a very uniform manner, reflecting off at the same angle at which the incident light struck it. This is known as specular reflection. The law of reflection governs this process, stating that the angle of incidence, the angle at which incoming light hits a surface, is equal to the angle of reflection, the angle at which the light leaves the surface. Because standard mirrors have a very flat surface, the law of reflection ensures that the light reflecting from them retains the same relative orientation as the incoming light. This is what allows mirrors to create a very precise image of whatever is in front of them. In contrast, if the surface were irregular or rough on a scale similar to the wavelength of light, the incoming light would be reflected in many directions, leading to diffuse reflection. This is what happens with materials like paper or unpolished wood, which do not create clear images because the reflected light is scattered in all directions. At the molecular level, the uniformity of the mirror's metallic surface facilitates the orderly reflection of light without altering its cohesive image-forming properties. This process happens incredibly quickly because light travels fast, approximately 299,792 kilometers per second, and the molecular interactions are almost instantaneous from our frame of reference. In summary, mirrors work at a molecular level by having a smooth metal coating that interacts with light. This interaction involves the oscillation of free electrons under the electromagnetic influence of light photons, which then emit the light at the same angle as it arrived. Accordingly, the meticulous design of a mirror ensures the preservation of the angles of incoming light, enabling it to cast back a perfect replication of the scene in front of it.